In our last presentation, we were tackling the problem of the motion of a gantry crane. The gantry crane is used in factories and on docks to move large loads. The way it works is as a trolley that moves across a rail. Suspended below the trolley is a load. The trolley undergoes a trapezoidal velocity profile, accelerating, then moving at constant velocity, then decelerating. The problem we wish to tackle is the swaying of the load at the end of the trolley's motion. Our goal is to move the trolley through a specified distance, d, and when the trolley has come to a stop at the end, to have no swing of the load. For this problem, the trolley and the load start at rest. So we know our initial conditions here are 0, and this is a zero-state problem. The input for this problem we label x of t, and it is the acceleration of the trolley. The output is y of t, and it is the angle of the line to the load. In our last presentation, we showed a simulation, and in this simulation we did move the desired distance, but there was considerable swinging of the load at the end. So the task we have before us is that of adjusting the timing of the segments of acceleration, coasting, and deceleration so that we move the specified distance, but have no swing at the end of motion. In our last presentation, we defined a solution method that had 6 steps, and we completed the first 2 of these steps. We found the transfer function between the acceleration of the trolley and the angle of the load. We also defined the acceleration and velocity profiles of the trolley in terms of timing parameters t-coast and t-accel. To summarize, we specified the velocity profile as trapezoidal, consisting of a period of acceleration to time t1, a period of constant velocity between time t1 and t2, and a period of deceleration from time t2 to t3. The acceleration and deceleration were done at the same rate. The times t1, t2, and t3 were related to the parameters of timing, t-acceleration, and t-coast. The area under this velocity profile was the distance traveled, which is specified in the problem, and therefore this provides an equation relating t-acceleration and t-coast. We view this equation as a constraint on the values that these parameters may take. With the first 2 steps of our solution method now completed, we'll move on to steps 3 through 6. We'll take the acceleration that we found in the last presentation and find its Laplace transform, x of s. We'll then multiply this by the transfer function that we found previously to find the output y of s. We'll inverse Laplace transform this to find y of t, and this y of t will be in terms of the timing parameters, t-acceleration and t-coast. We'll choose them in step 6 so as to make y of t 0 after the trolley has come to a stop. If you recall, our acceleration profile was a pulse of height a between time 0 and t1, and a pulse of negative height a between times t2 and t3. We can easily find x of t from this description. It's built out of unit steps that have been appropriately delayed. So x of t is equal to a times the quantity u of t minus u of t minus t1 minus a times the quantity u of t minus t2 minus u of t minus t3. Now, of course, the Laplace transform of a unit step is 1 over s, and the Laplace transform of a unit step that has been delayed by cap t seconds is e to the minus s cap t times 1 over s. So, using this concept, we can easily find the Laplace transform of x of t, and it will be x of s equals a times the quantity 1 over s minus e to the minus s t1 over s minus e to the minus s t2 over s plus e to the minus s t3 over s. So we have found x of s, and we had the transfer function h of s from before. So y of s will be h of s times x of s. H of s was 1 over ls squared plus g, and x of s was a over s times the quantity 1 minus e to the minus t1s minus e to the minus t2s plus e to the minus t3s. So we have y of s as shown here. Now let's define y1 of t as the inverse Laplace transform of 1 over ls squared plus g times a over s. Given that, we can then find y of t as follows. Y of t will be y1 of t minus y1 of t minus t1 minus y1 of t minus t2 plus y1 of t minus t3. I hope you see why this is true. When we find y1, what we're doing is we're finding the inverse Laplace transform of this first term. And then the other terms are just delayed versions of this. Since the system is time invariant, the responses to the other step changes will be the same as the response to the first step change, only delayed. Therefore, we only need to find the response to the first step change, y1, and then all the other step change responses will be delayed versions of this. So let's now find y1 of t by taking the inverse Laplace transform. This is not difficult to do. We'll partial fraction expand, and it will become a over g times 1 over s minus a over g times s over s squared plus g over l. We're now ready to go to the Laplace transform table to do the inverse transform. And we'll find y1 of t is equal to a over g u of t minus a over g cosine of square root of g over l t u of t. Here are some things to note about this solution for y1 of t. First, y of t is an angle, and therefore it is dimensionless. Since y1 of t is a portion of this, y1 of t also has units of angle, and is therefore dimensionless as well. So it's not surprising that we find the term a over g as the constant out front here. A and g both have units of acceleration, so a over g is unitless. Next, note the frequency that's present inside of the cosine. It is square root of g over l. You might remember from an elementary physics course that a pendulum has a frequency of square root of g over l. So it's not surprising to see that here too, as the load is a pendulum. Finally, I want you to recall that y1 of t is not the system response that we're looking for. It's just an intermediate step along the way. Before going on to solve for y of t, let's examine the signal y1 of t. If you remember, y1 of t is the response to the unit step input. It's the first step in acceleration occurring at time 0 that causes y1 of t. So y1 of t has a period of 2 pi over the square root of g over l. Square root of g over l, of course, is the frequency. And you'll note that it goes from 0 to 2a over g in terms of its maximum amplitude. Its average value is a over g. As we noted before, a over g is unitless, and y1 of t is an angle, also unitless. We found an expression for y1 of t before, and we also know that y of t is y1 of t minus y1 of t minus t1 minus y1 of t minus t2 plus y1 of t minus t3. So I can now solve for y of t. I simply need to take my expression for y1 of t and add it together with appropriately delayed versions of itself. That will then give me y of t, shown here. This is a complex expression, but you'll notice that the terms are similar to each other. They differ only in the amount of delay present in each term. We are particularly interested in the angle, y of t, after the trolley has stopped moving. This is for t greater than t3. In this case, y of t simplifies to the expression you find here. Notice that u of t and all the delayed versions of u of t in the previous expression are gone. This is because they are all 1 for t greater than t3. We now want to pick txl and tcost such that this is 0 for all t greater than t3. Recall that t1, t2, and t3 are related to txl and tcost. Thus, by picking txl and tcost, we are picking t1, t2, and t3 in the above expression. How can we choose these variables so that y of t will be equal to 0 for all time t greater than t3? We'll cover how to do that in our next presentation.